This is hacking mobile devices, and we're down towards the end. There's about 3 classes left. And so we're going to talk about analyzing iOS applications, and then I have a demo of the Metasploit taking over an Android phone. I got that. That's working well, so that's the thing you ought to do. So let's take a look at analyzing iOS apps, part 2, the data protection API. Oh, and let me get my projector running here. At least I didn't realize it wasn't running. Anyway, all right, so we'll talk about the data protection API, the keychain, and a couple other things here. So here's a report from, I guess, 14 years ago now. Citigroup, there's iPhone app, put user information in a hidden file, and that could be exposed. It could be used by attackers to gain unauthorized access. So, by the way, did Canonical. The people that made the Nessus scanner, their Android app just stored the password in plain text on the SD card where other apps could find it. A lot of people make these mistakes on mobile devices, putting sensitive information in a one-wise place. So in iOS, however, it is now not that vulnerable. I quit reporting storage of plain text credentials in iOS apps as a vulnerability because the operating system protects them so well that I really don't think there's a significant risk. They have so many layers of encryption. Every file has an encryption key, which is locked by a protection class. You specify what protection class you want, and there is a secure enclave managing the keys, which is a protected area that can do cryptographic coprocessing, but is not part of the memory space of the processor, like a trusted platform module on Windows. So it all starts when you log in with a passcode key. So you type in your passcode, and that is used to generate a key with password-based key derivation, which is just hashing. And then it takes your input passcode and a device-specific key to make a key which is unique to your device. And the key, the device-specific key, is embedded in the hardware-based crypto accelerator. So again, that can't be stolen by any kind of malware on the phone. So that's the point. You have a unique key which depends on your password and on the specific phone you're putting it on, which is the unique key to get you going. And then you have layers of protection. So in comes your passcode, in comes from the universal ID key from the protected area of the device. That creates a passcode key. And then you have a device key. And then you calculate various keys from those, and you use those to represent the various security levels. And you can have no protection. You can have things here that have no further encryption, although I think they're still encrypted by like the passcode or something. We'll talk about they're encrypted on the device, but not by the passcode. Then there's things that are complete until first user authentication. These are things that are protected at rest, but once you log in with your PIN, then they're unencrypted. And here's the things that are totally encrypted. You have to enter your PIN to see them. And so here's the layers. No protection, not encrypted. Complete protection, inaccessible when the device is locked. Complete unless open. So it's unencrypted when the device, if it's in use, it stays unencrypted when the device is locked. Your various types of level, complete until first authentication, encrypted only from boot up to the first unlock. So this is the idea. If you lose your phone, it will be locked, and the person won't have your key, so they won't be able to get to this. This is the default setting. This is normally what you want. Once you log in with your PIN, then you want to have access to everything with no further restrictions. That's just, of course, the logical default, but if someone steals your phone, or they find it, or you lose it somewhere, and it's locked, then all your stuff is encrypted and they can't get in without your passcode. So there's a keychain to manage all this. And it's got a lot of protection classes for data stored in the keychain. Here's something that's always accessible. Here's things that are accessible only after the device is unlocked. Here's only after the first unlock from boot. And there's more layers. Always accessible but can't be sent to another device. Always accessible when it's unlocked. Accessible after the first unlock. And this only allows you to store the items if there's a passcode on the device. Various levels of security are available to store things in the keychain. And I know my Mac stores things in the keychain, and then it shares it with my phone. And it shares it with my other Mac. So I think the default shares it with your other iOS devices, as long as you're logged into them all. So you can prevent access to keychain when no passcode is set on the device. I haven't noticed this in iOS devices. I've never tried to use an iOS device with no passcode. I don't even know if you can do that anymore. I know you can do it on Android. You can have an Android device, at least in the emulator, with no passcode. But if you do, then at least earlier versions would not let you put in any custom certificates. You had to put in a passcode to do that. So it's a SQLite database, and there's a tool called Keychain Dumper that will dump out the contents of it, but of course that assumes you have a jailbroken device, and you must of course have decrypted it. So you'd have to set it to one of those protection classes where you've logged in knowing your PIN. But the point is it will just let you see the data. All right. And then of course you might not use a PIN. I certainly don't anymore now. Do I use a PIN? I feel like I do on my real phone. It has a PIN and it has, I think, face recognition. It has both, but it keeps on making me put in the PIN. So if Touch ID is enabled with a fingerprint reader, which I don't think I have on my phone, but I guess it was on the earlier ones, then there's a secure enclave holds the data protection class keys, and when your Touch ID is enabled, the keys are held in memory, wrapped in another key that you can only get from the Touch ID. So your fingerprint is read like a password. It is then somehow converted into a key by some kind of password-based key derivation system, and then it uses that to open the wrapping key and get to the key to decrypt the data. So Chaos Computer Club broke Touch ID in 2013, about 10 years ago. They found a way to bypass it. They were able to just take a fingerprint from a glass and make a fake finger that would open it. And this is an issue. I know there was, this is a problem with face recognition, and a problem with fingerprint recognition is that there are photographs of people, and maybe that would be good enough to fool the face recognition, and your fingerprints are being left everywhere. So arguably they're both not terribly secure. Although what I have read is that the Apple iPhone face recognition is not just taking like a photograph of you at all. It's sending, I think, an infrared beam, and it's scanning your face in 3 dimensions to get an accurate thing. And the thing I've noticed is it works. Fingerprint recognition does not work on any Apple devices for me. I don't appear to be a normal human. I can train it, and it works for like a couple of days, and then it doesn't work again. I think maybe my fingers are too big and I can't find the right spot. I've tried different fingers, I've tried different techniques. It just doesn't work at all on any Apple device. But facial recognition works very well on the iPhone. So anyway, all right. Also, I can't use Apple earbuds. They just fall out of my ears. I don't appear to be a human. Anyway, everybody else uses them. I can't understand how. I can't get any good out of them at all. I get British earbuds that work. Anyway, so iOS binaries, you can reverse engineer them to some extent, like we've done with Android, but it's a whole lot more difficult. Now, they are Mach-O binaries. Microsoft executable files are portable executables, PEs. They're EXEs and DILs usually. And Linux files are ELF files, executable link format. That's the binary format of the file that runs. And on iOS, it is Mach-O. So it's got a header, and it's got commands that load the file, and then it has the layout determining the sections and the symbols and the data. So it looks like this. You got the header, the load commands, various segments, various sections of data. To some extent, like the other ones, there's different segments of the file, places for code, places for data, and so on. And then there are fat binaries that contain multiple Mach-O files, so they support different architectures. So you might support ARM7, ARM64, the big type. And so OTool is the tool to examine these. So if they use OTool and examine an app, they find that it has a CPU type of 16 million and another CPU type of 9. And this ARM64 is this one, 16 million, and this is one of the ARM 32-bit versions. So it's got both of those in there. And as I showed you, I think last time, when we went into the password manager, Android apps typically have like 4 architectures there. They have x86, x64, and ARM, all in the Android app. The same kind of reason. So here they are, CPU type and subtype for ARM, 32-bit ARM of various versions, and then ARM 64-bit. So you can, if you want to, you can take a fat app that has multiple architectures, and you can remove just one architecture out of it to have a single architecture app, which is not what you would want if you were distributing it for many phones, but you might want it to analyze it. I see a comment in the chat. Maybe you burned off your fingerprints. I know, not that I know of, but yeah, something like that. All right, so Lipo is the tool that can take a fat binary and turn it into a skinny binary with only one app in it. So, all right. And so then there's security-related features, and these, by the way, should be familiar if you've taken the exploit development class. These are the same generic security features you find in every operating system these days. Address-based layout randomization, came out maybe 10 or 15 years ago, about the time Windows XP went to Windows Vista, where instead of, it used to be, up until that time, maybe around 2003 or so, you would load a program, all the operating system would do is look at the first available piece of memory and put it there. And then the next program would go to the next one, so you could pretty much guess where a program is loaded. If you had a server, like a web server running IIS, you could just build your own server using IIS and see where it is in memory and predict where it would be at the other end. I see more comments. Fingerprint authentication is insecure on iOS and maybe Android too. Well, people have found a few exploits. Certainly, I would think fingerprint authentication is probably insecure in anything because you're leaving your fingerprint everywhere. So just taking a glass you've handled or anything, we can get a copy of your fingerprint. So I would think that's a weakness, yes. I think, and I think by the same argument, facial recognition is probably insecure. It doesn't seem like a flat photograph would do, but I think you could take like a video, like the one I'm making right now, where I turn my head, and I'm sure you could make a 3D model of my head and make a good enough thing to fool facial recognition. If you wanted to, it probably wouldn't be that difficult for somebody with like theater skills. All right, so address space layout randomization is the modern technique where every time you launch a program, it randomly relocates it in memory. And the only point of that is that if you have a memory corruption exploit, like a buffer overflow, where you can feed in addresses, data that is interpreted as an address, you don't know where to point the code to find your code because you don't know where your code lives. So this is a strong defense. It stopped the whole generation of buffer overflow exploits up through like Windows XP, and iOS has it too. In order for this to work, each program has to be compiled as a position-independent executable. It's a command line switch for the compiler, and that means store basically a relocation table with it, so if there are any hard-coded addresses in the compiled machine code, keep track of how to rearrange them to adjust for loading in a different area of memory. If you have old apps that were compiled without this feature, then even if your operating system supports address space layout randomization, the app cannot use it. It must load at a specific memory location. But ever since iOS 5, all the built-in apps have position-independent execution. Stack smashing is another defense, been around at the same time. This is where, when you have a stack, which has all the local variables used in your subroutine, you put a canary value, the operating system does, before the end of the stack frame. So if you have a buffer overflow and you start writing to memory locations that you're not supposed to write to, before you can hit a memory location that's used for the return address, you will break the canary, so the canary value being altered will be detected, and the program will simply stop with an error message instead of using the corrupted data, which would give the attacker control of the machine. So it's a very common form of defense in all modern operating systems, and iOS has it too. Automatic reference counting is one I haven't heard used on Linux. I probably is some equivalent there, but what this does is reduce use after free and double free vulnerabilities. This is one of the great things about Rust. Rust, if you allocate memory on the heap, you just allocate the variable, and as soon as the variable goes out of scope, it's automatically freed. So you don't have to manually free it. But unfortunately, in C, you have to allocate memory with malloc and free it with free, and therefore you can make the mistake of forgetting to free it, so you have a dangling pointer, or freeing it twice. So you end up having a write operation on memory that was not properly initialized, and both of those can be used to take over the box. So this automatic reference counting will do something like count how many times you've allocated memory and make sure that you freed it once for each time and no more, that sort of thing. All right, so your App Store, the stuff you get from the Apple App Store is encrypted. They're all encrypted with digital rights management. They're decrypted at runtime by the loader. So if you want to decrypt it, in order to get a decrypted copy of the app to analyze, first you have to put the app on a phone, then use GDB attach to the phone, find the base address with this command, retrieve the memory segment, and write the decrypted segment over the original encrypted segment. This is what you have to do to get an app off the phone and decrypt it and get a decrypted version. And there are automatic tools to do this. It's quite difficult. Like I say, I used to do it in this class years ago, but it really only way to teach it would be if I had a lab with a bunch of phones that were all the same, and you did everything right in the lab. You have to have an iOS, you have to have an Apple Mac device, and you have to have a phone, and they both have to be of a known version, so you can do these things. It's quite difficult. There's other decryption processes. There's class dump, which will show you the details about internal classes, methods, and variables. It doesn't give you the complete code. It gives you the named locations, which gives you some idea what's going on. And you'll see it here. Here's the Starbucks app. If you take it apart, you'll just see the name of all these things: guest checkout, digital card, default parameters, replace card, and so on. Is password card. You're just getting the labels. So you get a little bit of information about what's in there, but not the whole code. However, you can get the whole code and then you analyze it with Hopper. Hopper is a decompiler like IDA Pro. It runs on the Mac and it can decompile iOS apps. And so I had projects where people did this, but it was very, very difficult to do. Anyway, that's what it looks like. It looks like IDA Pro. And I say these projects were not much fun, and I haven't stuck with them. But that's the tool you use if you want to do this yourself. If you're not trying to make something for a class where all these students are going to try to do it with different equipment, which is what stops me. If you want to just get it yourself, these are some of the tools you would get, and then you would just get it all set up to work on your Mac and your phone. And that's what, of course, the developers and hackers do. They have their own setup where they've got it working on their versions of things, and then they can analyze apps. So let's try a Kahoot. Should be here. 2B, there we are. It's a shame we can't do more iOS. The only thing that would work is if there was a cheap or free iOS emulator we could get, like these Androids, but there's nothing like that. The only stuff that's available is really expensive. All right, so which key is controlled by Touch ID? Wrapping key that's used to wrap another key in memory. That's how it's implemented. All right, what is the file format for iOS apps? They call it. I don't know why they don't just use ELF, because it's essentially Linux, but they use this thing called Mach-O. All right, what key is embedded in the hardware-based crypto accelerator? Called the UID key. All right. And what feature mitigates heap corruption vulnerabilities? Automatic reference counting, ARC.